students, welcome back to another lecture in our course Environmental Modeling and Simulation. In the previous lecture, we were talking about limit cycles, and an example that we were exploring was the example of glycolysis. If you remember, glycolysis is an essential function of living organisms by which they break down glucose to produce energy. And our model was modeling the relationship between the levels of ADP and F6P, which is adenosine diphosphate and fructose 6 phosphate. And our model looked something like this. And if we look at this model, X here represents, this is a non-dimensionalized version of the model. In this, the X is associated with the levels of ADP or adenosine diphosphate, and Y is associated with levels of F6P or fructose 6 phosphate. And what we managed to do in the previous lecture was to draw nullines for this system. Now, as a reminder, X nullline is basically when dx by dt is equal to 0. And then the y nullline is when dy by dt is equal to 0. So, we drew x nullline and y nullline, and the graph that we got is the graph on the right side of this slide. So, another fascinating thing that we did in the last lecture was look at the direction of flow just on the basis of nullline. The red arrows here show you the direction of the flow around the nullines in the areas that are segmented by the nullline. There is one arrow that needs to be read. Here we are. There we go. And then the highlighted gray portion, is the trapping region. Now, I define trapping region as a region where any trajectory, if it lies there, will not be able to escape it. Now, since within the trapping region, we have a fixed point for sure. The two nullines are clearly intersecting here. So, we definitely have a fixed point. Now, we do not know, however, what kind of fixed point it is, whether it is stable, unstable, whether we are dealing with the center or we are dealing with a situation where we have an orbit. These things are still not clear, but we do know that there is an intersection point of nullline. We also know this is a trapping region. And now what we are going to do is we are going to understand this particular fixed point better to understand whether it is a center, a stable or unstable fixed point, or if it is indicative of a orbit, so limit cycle. So, the way we are going to go ahead with analyzing this system further is to use the Jacobian, the method that we have done for simpler 2D linear and nonlinear systems. So, Jacobian for this model, let us find it out. Typically, the first step when you are solving these 2D systems or multiple dimension systems, nonlinear systems, before finding Jacobian, I like to find the fixed points. But I know in this case, finding fixed point is going to involve certain amount of calculations. I have already calculated it for you, and I am not going to go ahead and find the fixed points first, but that is typically the first step. So, remember what the Jacobian of this system would look like. First, let us say this is the first function and this is the second function. We want to find the partial derivative of f with respect to x. So, what we end up here is minus 1, this will become 0 and this will become 2xy, and then with respect to y, so we will get a plus x square, and then here we are deriving partial derivatives of g with respect to x and then with respect to y. So, this is our Jacobian, and now we want to find the fixed points. As I mentioned just now, that finding the fixed points of the system means dx by dt and dy by dt should be simultaneously equal to 0, which is quite a calculation. So, what I have done is I have already calculated the fixed point and I will just give it to you. So, the fixed point for this system is basically we know there is one fixed point because the nullines intersect only at one position, and I have written them separately because this is a slightly interesting fixed point. It's not very simple like 1 and 0 or 1 1 2 1, like the kinds of fixed points we have seen in case of Lotka-Volterra family of models. Okay, so this is our fixed point. Now we want to find out the characteristic equation at this fixed point. So all we need to do is substitute the value of x and the value of y in this Jacobian, and we'll get the characteristic equation. Again, this involves a lengthy calculation, and I'll skip that to be more economic and wise about our time together. Once you put the value, you will get very easily the value of trace of the characteristic equation and of the determinant. Trace and the determinant, you can get it from the characteristic equation. Now determinant in this situation, in this system, is very simple. It is equal to a plus b square. Now since we are assuming that both a and b are positive, I mean, it doesn't matter if b is positive, it's definitely a real number. It has a real value, no imaginary parts. So we know that a plus b square is always going to be positive. So if you remember our diagram, so if you look at our diagram, we are dealing with a situation where delta is definitely positive. So we are not dealing with a saddle point. So right here we know that whatever this intersection of the null points is, it is not a saddle. Now let us find out whether it is a stable area or it's an unstable area. Basically, the intersection of null lines, is it an attractor or is it a repeller? I must pause here to tell you that very interesting things happen within a trapping region. You might have a fixed point in the trapping region. In that case, Poincare-Bendixson theorem does not apply. You may not have a fixed point in the trapping region, in which case there's going to be a limit cycle. Another possibility, which is not what we are going to cover in this course, however, is that we might have a strange attractor. So strange attractor is an interesting geometrical feature that attracts trajectories towards itself, and it's very sensitive to tiny changes in the initial condition. Now, if your wheels are turning and it reminds you of chaos, then you're on the right track, because chaos is associated with periodic functions that are very sensitive to tiny changes in initial condition, which is what can happen within a trapping region. But we are not going to talk about that. We are going to stick with relatively easier to model and quite versatile 2D nonlinear systems where nothing much happens within the trapping region except presence of an orbit or a stable or unstable fixed point. Okay, now here we know that delta is equal to a plus b square, so we are not dealing with saddle node. Now we definitely need to look at the tau value. Now the trace, once you put in these values of x fixed point into the Jacobian, the trace comes out to be an interesting equation. So I'm going to take time to write it down here. So this is the value of your trace. Now depending upon the value of trace, like if you know the value of a and b, if your trace is greater than 0, equal to 0, or trace is less than 0, will determine whether the intersection of null line is a stable area or an unstable area. Basically, is it an attractor or is it a repeller? Now, if you go back to our diagram, we know that our delta is definitely positive. Now, if our tau is positive, then we are in the domain of unstability. If our tau is negative, then we are in the domain of stability. And if our tau is equal to 0, then we are dealing with the center. So, the critical value of tau here is 0. So, what happens when we make our tau 0 here? So, if we set this equal to 0, we get a very interesting critical value of critical situation where our system, our intersection of the two null lines is transitioning from stable to unstable or vice versa. And when you put tau is equal to 0, what we get is that b square is equal to half 1 minus 2a plus minus root 1 minus 8a. So we know that this is the curve. And don't worry, in the exam I will not ask you to do these lengthy equations. It's just a demonstration, and it's also a very important model that has been used in various systems, including environmental systems. Okay, so we get this system for tau is equal to 0. Now what that means is that the area defined by this curve in a graph of a and b will determine the stability of, will determine for what conditions of a and b are we having a stable intersection, an intersection of null lines that is stable versus unstable. The graph that, this particular equation looks something like this. If we plot b versus a and try to plot this graph here, it looks something like this. Now the inside region, which is enclosed by this curve, is the region related to tau greater than 0. Here we have tau equal to 0 and here we have tau less than 0. So basically inside the curve we are dealing with either an unstable fixed point, but as it also turns out, a stable limit cycle. And then of course tau equal to 0, we are dealing with the center, and then tau less than 0, we are dealing with a stable fixed point, or a stable fixed point. Okay, now clearly by looking at the A versus B diagram, it appears that within the curve, when tau is greater than 0, we are dealing with a situation where you have an unstable fixed point. What we also notice is that this is also the region where we have stable limit cycle. And if we draw this, if we use computational models to draw this, what we see is that the flow lines actually look like so. What we see is that actually there is a orbit here, and I'll draw the diagram again for clarity. So we have x here, we have y here, and we are going to draw the x and y null line. So this is our x null line. This is our y null line. And this is our trapping region. And if you remember from previous lecture, we established that the direction of flow, looks something like this. So when we model this mathematically, we actually see that there exists an orbit here, and this is a stable limit cycle. And now this is interesting thing about a stable limit cycle. If you remember when we are in our first lecture of limit cycle, if this is a stable limit cycle, what this is telling you is that within the limit cycle, the trajectories will move away from whatever their origin is, and eventually they will join the limit cycle, right? And trajectories outside the limit cycle will slowly converge into the limit cycle. So this is the behavior of a stable limit cycle. Now what we see here is that this is the trapping region. The fixed point we know is unstable when tau is greater than 0, which is when it is inside the curve that I showed you here, this region. So what happens is any trajectory at the intersection of null lines or around it will eventually move further away from the intersection and then join the limit cycle. Any trajectory outside the limit cycle will move closer and closer to the orbit until it becomes one with the limit cycle. So even computationally we see this is exactly what happens. There is definitely a stable limit cycle here. So to summarize, what we did in this system is we drew null lines to help us understand the flow around the intersection of null lines. We used null lines to understand the flow around the intersection of the null lines, to understand the trajectories, the flow of trajectories in the phase portrait. Once we had a clearer picture of how the trajectories are flowing, we solved it using Jacobian to understand the stability of the intersection, which we found was an unstable fixed point when tau is bigger than 0. Again, clearly, as the values of A and B change, the unstable fixed point might turn into a stable fixed point. The stable limit cycle might disappear or turn into an unstable limit cycle. So clearly, the behavior of the intersection of the null lines, the behavior of the trajectories around it will vary as A and B vary. But for the right A and B that is within this curve, the hashed portion of this curve here, we have a stable limit cycle. Now remember this thing, within a stable limit cycle, so let's say this thicker orbit represents your stable limit cycle. Within any trajectory inside this stable limit cycle will slowly move away from its origin and end up on the limit cycle. Any trajectory outside it, because this is a stable limit cycle, will finally converge towards the orbit and become one with it. So students, this is all we have for limit cycles today. So students, this is all we are going to discuss about limit cycles for now. And now we are going to look into bifurcations. Bifurcations. If you remember our lectures initially on bifurcation, we spent a lot of time trying to understand one-dimensional bifurcation. And the three major categories of bifurcations that we studied were saddle node, bifurcation, where fixed points either appear or disappear. It has many different names. Blue sky bifurcation. It has many different names such as blue sky bifurcation. The other kind of bifurcation that we spent quite amount of time was transcritical bifurcation. Transcritical bifurcation happens when there's always one constant fixed point and the other fixed point collapses into this constant fixed point and then emerges again. However, they switch their stability, the fixed points switch their flexibility around the critical point. And the third kind of bifurcation that we talked about was pitchfork bifurcation. We also spent some time discussing imperfections in bifurcation. And we studied insect model, and we are going to revisit that model when we talk about bifurcations now in 2D systems. In 2D systems, bifurcations behave very similarly to 1D system. Basically, as one of the parameters is changing, the fixed points will appear or disappear in case of 2D saddle node bifurcation, or they will switch their stability in case of 2D transcritical bifurcation, or we'll have a very classical pitchfork bifurcation diagram in case of 2D pitchfork bifurcation. However, in case of 2D bifurcations, we have other kinds of bifurcations too that we'll be discussing in the upcoming lectures, like Hoff bifurcation, which is very important. Let's start with saddle node bifurcation. In 1D system, for our saddle node bifurcation, a typical example that we used was this one. dx by dt is equal to a minus x square. Now, in this case, as a revision, remember as a varies, the number of fixed points also vary. Let's say when a is less than 0, what happens? When a is less than 0, what we get is no fixed point. So, the curve here will not have a fixed point, and the 1D phase portrait will look something like this. No fixed point. Now, as we increase the value of a, so let's say a is equal to 0. Now, when a becomes equal to 0, there appears the first fixed point, which is tangential to the x-axis. And then as a becomes greater than 0, now two fixed points appear. So, this was a classical example of saddle node bifurcation, where two new fixed points appeared. Now, in a 2D system, we can use the exact same model, but just add another variable. And of course, I'm going to keep it very simple. And then for the y-axis, the second variable, let's just make a very simple model minus y. So, we know that the y is reducing for positive y, increasing for negative y. So, it's moving towards the x-axis. So, let's explore this very system model and try to understand how saddle node bifurcations look in 2D. So, let's start with a very simple situation of a bigger than 0, greater than 0. If a is greater than 0, remember step 1 is to find the fixed points. So, the fixed points would be x is equal to plus minus under root a and y is always equal to 0. So, we have two fixed points here, one is root a 0, another is minus a 0. So, if this is our phase portrait, x on the x-axis and y on the y-axis, one fixed point is here minus root a 0, another fixed point is here root a 0. Now, in order to find the stability of this system, let's find the Jacobian. So, that's the step 2. So, the Jacobian of this system is very simple. Let's say this is the first function, this is the second function. We need to find partial derivatives of them with respect to x and y. By the way, we can also use null-Klein methods for this, but I want to go through the Jacobian. Hopefully, it will be a good revision for you. So, this is our Jacobian, and then for our characteristic equation at minus root a 0 so here if we look at the trace is 2 root a minus 1, the determinant is minus 2 root a. So, determinant is less than 0 and we don't know if trace is positive or negative, but determinant is negative for sure. What is telling me is that this is saddle node. So minus a root 0, this node is a saddle node. Now let's look at root a0. So for root a0, the characteristic equation will look like this. Now here our determinant is 2 root a, it is positive. So we know that we are on the first or the fourth quadrant, so we are either in a stable or unstable situation, we are not dealing with saddle node. Now trace will determine, the value of trace will determine whether we are in a situation where we have stable node or stable spirals, or unstable node or unstable spiral. So the trace here is minus 2 root a minus 1, which clearly is less than 0. So we are dealing with a negative trace. So now next step is we want to find out tau square minus 4 delta to see if our eigenvalues are real or complex. So tau square minus 4 delta, so this is tau is negative, so remember we are dealing with stable. So now we are in the fourth quadrant. So we see that tau square minus 4 delta is actually square of 2a minus 1, which is always going to be positive. So we are outside the curve, we are dealing with stable node. Here, as long as a is positive, we have two fixed points, one of them is a saddle node and one of them is a stable node. So stable node means it's attracting in all direction, and a saddle node, it means it has a stable manifold and an unstable manifold. So let's go ahead and find out, we need to find out eigenvectors and eigenvalues for the saddle node. So our Jacobian is minus 2x. This is our Jacobian. So we are trying to find out the eigenvalues for minus root a 0. So and then to find the eigenvalues, determinant of this should be equal to 0. So clearly we have two eigenvalues. One of them is 2 root a and the other one is minus 1. Okay, so this is saddle, this is positive, this is negative. Clearly now we want to find corresponding eigenvectors. So let's first find out for 2 root a. So what we get is 0, 0, 0, 0. So basically what we'll get is V2 is equal to 0. So the positive eigenvalue corresponds to V2 equal to 0. V2 equal to 0 means we are dealing with x-axis, eigenvector in direction of x-axis. Now similarly for minus 1, what we'll get is that V1 is equal to 0. Very simple, just substitute minus 1 instead of lambda here and then do the product with the eigenvector, equate equal to 0 and you'll get the values. So this is corresponding to lambda is equal to 2 root a and this is corresponding to lambda is equal to minus 1. So clearly for our saddle node here, minus root a is 0, one eigenvector points in this direction and one in this one. The stable eigenvector, which is a stable manifold, points in direction of y-axis and here corresponding lambda is minus 1. The unstable manifold points in the direction of x-axis and the lambda corresponding lambda is 2 root a. And here we have a stable fixed point at root a 0. Already we can see how the lines will look like, how the flow lines will look like around, and clearly this is an attractor. Now similarly if we find the eigenvectors and eigenvalues corresponding to the stable node, which is also important, what we will get is also that eigenvectors are like so, Now, depending upon the value of A, this is important, so I want to spend 2 minutes on this, because remember, the trajectories will be tangential in case of a stable or an unstable node to the slower eigenvector. So, we need to know whether they are tangential to x-axis or tangential in the direction of y-axis. So, let us try to find out the eigenvectors and eigenvalue around root A0. So, again our characteristic equation for root A0 is and then so we have lambda is equal to minus 2 root A and lambda is equal to minus 1 as our eigenvalues. Corresponding eigenvector would be given by this. Let us find out eigenvector first for minus 2 root A. So, for minus 2 root A, the corresponding eigenvector is given by V2 equal to 0. Now, let us find out the eigenvector corresponding to minus 1. So, for eigenvalue is equal to minus 1, our eigenvector would be given by this. Which gives us V1 is equal to 0. So, this is V1 is equal to 0. So, now we can finish our phase portrait here. At V1 equal to 0, which means in line with the y-axis, it is minus 1. So, lambda here is minus 1, and with in line with x-axis, the lambda is given by minus 2 root A. So, we need to know which is the slower eigenvector. Now, if minus 1 is bigger than minus 2 root A, or 1 is less than 2 root A, or root A is less than 1 by 2. So, it depends upon the value of A. Then the slower eigenvector is minus root 2A. So, the curves, the trajectories will look like this. Tangential to the slower eigenvector. However, if that is not the case, instead of being tangential to the x-axis, if the situation is different, where minus 1 is less than minus root 2A, so now we can look at the relative values of corresponding eigenvalues and figure out which eigenvector the trajectories would be tangential to. So, in one place we have the magnitude of lambda is 1, and in another eigenvector the magnitude of lambda is root 2A. So, if 1 is more than root 2A, then root 2A is the slower eigenvector, which means that the trajectories will be tangential to the eigenvector corresponding to minus root 2A. So, it will look like this. However, if that is not the case and we have a situation where 1 is less than 2A, so 1 is a slower eigenvector. In that case, trajectories would be tangential to the slower eigenvector, which is parallel to y-axis. Now, this is all for today's lecture. In the next lecture, we are going to look at what happens when A is equal to 0 and when A is less than 0, and how this saddle node bifurcation eventually looks like in 2D. Thank you.